Greetings and welcome to Distillate. Now we'll be starting with our second chemical engineering subject, which is thermodynamics. So thermodynamics is a very vast area. It covers a very vast domain. So I have divided thermodynamics into two parts. The first part is going to be your elementary thermodynamics. So in this part, you will be studying about basic concepts, somewhat some of the things that people might have gone through in class 12th, class 11th and 12th, then certain different concepts as well. We'll be studying about those things. And after that, we'll be dealing with laws of thermodynamics, then concepts associated with those laws, variables associated with those laws. All right. And the second subject is the second part into which I have divided it. It is chemical engineering thermodynamics. So here you will be dealing with specific relations that are specific to chemical engineering. All right. So here you'll be dealing with a lot of different and very important concepts. You'll be dealing with fugacity, you'll be dealing with the chemical reaction thermodynamics, people will be dealing with solution thermodynamics, phase equilibrium thermodynamics. So all that we'll be covering in chemical engineering thermodynamics. All right, so altogether these two form the entire thermodynamics that is generally taught to chemical engineering students. All right. So make sure that you're clear with concepts taught in engineering thermodynamics before you switch to chemical engineering thermodynamics, because this is definitely a very complicated subject. So on top of that, if you have your basics weak, if you are confused with your basic concepts, then you're going to face a lot of problems. So please make sure that your basics, your elementary thermodynamics is perfect before you switch over to chemical engineering thermodynamics. All right. So once we've discussed all this, let's start with elementary thermodynamics. So when we start with thermodynamics, the first thing that you have to keep in mind is a few basic definitions. You will be coming across these terms quite a lot. So let's start with it. System. System is basically the part of the universe on which our calculations would be based. So whatever our calculations are going to be based on, that is going to be a system. All right. For example, if I have to deal with boiling of water, right? If I have to deal with boiling of water. So our calculations are based on this water, right? So this is going to be our system. All right, this water, it's going to be our system. Okay, surroundings is anything other than system. Anything apart from the system, the entire universe is known as the surroundings. And system boundary is a hypothetical boundary. It may be hypothetical, it may be physical. So boundary which separates the system and surroundings. All right. Anything that separates the system from its surroundings, that is your boundary. Okay. So here you can see this pink box that I have shown. This is your system. All right. Then apart from the system, rest of the universe is your surroundings. And whatever is separating the system from these surroundings, it's the system boundary. All right. Types of system comprise of open, closed, and isolated systems. So an open system, heat and mass both can be transferred. Okay, both heat and mass can be transferred in case of open system. In closed system, only heat transfer can take place, mass transfer cannot take place. All right, and in an isolated system, neither heat can be transferred nor mass can be transferred. All right, so these are three important systems: open, closed, and isolated systems. Then basic definitions in basic definitions, a very important concept comes, that is thermodynamic variables. So these are somewhat quite a lot of variables that you'll be using in thermodynamics in elementary as well as chemical engineering thermodynamics. We'll be dealing with somewhat these variables. Apart, so there are certain variables which I have not mentioned, of course, but most of them I have mentioned over here. So there's not much to inform about this slide because half of them we've already discussed in the first video, that was chemical engineering variables. For example, mass, volume, pressure, temperature, right? Then certain moles, mole fraction, density, concentration, right? And there are certain variables that you really don't have enough idea about. So there's not much to discuss about this slide. But yeah, these are somewhat quite the variables that you'll be using. So as we'll go through the course, we'll be studying about each and every variable more in detail. Okay. Then we move to state and path variables. Okay. So state variables are basically the variables that define the state of a particular system. Okay. State variables are some variables that define the state of a particular system. They, if the state of the system changes, then these variables will also change. Okay. So consider the following statement. CO2 is contained in a steel container. Now, if I simply give you this statement, and there's nothing much you can acquire, you can derive from this statement. All right, you don't even know whether it is liquid or gas. You only know that your system is CO2. And of course, you can get the properties of carbon dioxide. But again, properties of carbon dioxide vary at temperatures, different temperatures and different pressures. So you can really not get enough data from this particular statement. So we don't have any information about the system, right? We only know that carbon dioxide is a system. That's all. But let's say I alter the statement slightly and I say that carbon dioxide is contained in a steel container, maintained at 2 bar pressure and 327 Kelvin. When we talked about bar, let me tell you, bar, as we discussed, it is 10 to the power 5 Pascal, and 1 Pascal is equal to 1 Newton per meter square. Right. So this we discussed. Right. So 2 bar pressure and 327 Kelvin. Now we can definitely calculate. We have temperature and pressure. So first of all, we can get different properties of carbon dioxide, for example, its density, right? Then we can also get the molar volume. Molar, since we have pressure and temperature, therefore we can get volume per mole, right? Volume per mole, volume occupied by a single mole. And then we can also calculate its enthalpy, internal energy, etc. These variables we've not really introduced, so I'll not just get into too much detail for now. But yes, you can, in simple terms, you can say that you can express a lot, you can get a lot of information about the system just by adding the pressure and temperature of the system, right? Just by adding the pressure and temperature of the system, you can get a lot of information about the system. All right. So the difference in the two conditions is that in the first condition, we did not have enough information to understand the state of carbon dioxide in the container. In the second statement, we have enough information to interpret what is the state of carbon dioxide in the container. All right. So a state is a unique condition of the system which exists only for one particular set of variables. Okay. For example, if I'm saying that carbon dioxide at 2 bar and 350 Kelvin, then it can be only in one particular state. If I change pressure or temperature, its state would also change, right? The variables that define the state of the system are referred as state variables. So for example, if I say that my system is in state 1 and I have its variables P1 and T1, right? If I have this as the condition, then from here, if I take my system to state 2, then I cannot say that the variables are going to be P1 and T1. It might be possible that one of them might be the same, but all the variables, they cannot be same, right? So these variables which change as the state of the system changes, these kind of variables are state variables. All right, these variables are state variables. So all the variables of one state cannot be the same at the other state. One or the other variable has to change. One or the other state variable has to change. Okay. So in the above example, pressure and temperature are of course state variables, right? A basic minimum number of variables are required to define the state of a system. This is calculated on the basis of Gibbs phase rule and is known as degrees of freedom, right? So the degrees of freedom or the phase rule is basically that F is equal to C minus P plus 2, where F is known as the degrees of freedom. C is the components. P is the phases, right? So that's how you get the degrees of freedom. So basically that tells you the number of independent variables on which the properties of the system depend. Don't go to this statement. Let's actually give it that a minimum number of variables, the minimum number of variables required to define the state of system are your degrees of freedom, right? So for example, if let's say you have a system which is let's say which is a mixture of liquid as well as vapor. There is vapor and liquid and both are under equilibrium, right? Vapor liquid equilibrium. We have discussed about this, VLE. We have discussed what the basics of VLE were, right? So let's say I have pure water, but it is in a mixture. It is in vapor state and liquid state, and both are under equilibrium, are in equilibrium with each other, right? So in that case, the degrees of freedom, since we have only one component, that is water, two phases, that is vapor and liquid, and of course plus 2. So this gives us F equals to 1, right? So that therefore you need at least one variable. Minimum one variable is required to define the state of a system. All right, if you have nothing, if you simply say have water and in vapor liquid equilibrium, nobody would be able to interpret enough information about that. You need one variable, minimum one variable. You can get the pressure, the temperature, whatever. One variable would be required to interpret that, okay, from the pressure you can get the temperature, volume, and different things. But at least one variable you need. Okay. Then similarly, let's say you have a mixture. Let's say in vapor liquid equilibrium, you have a mixture of A and B. You have a mixture of two variables, A and B. So if that goes, then you have two components, two phases, and again plus 2. So you get F equals to 2. So here you will be requiring the pressure as well as some other variable. So this you can understand, we discussed about Raoult's law in one of the lectures. So in Raoult's law, if you simply have the total pressure of the system, would you be able to derive that, okay, this much amount of A is there in the liquid phase, this much amount of A is there in the vapor phase? No, not really. But let's say if I give you one of the variables. So in vapor liquid equilibrium, if you remember, we had variables X, Y, partial pressure, right? All these were my variables. And saturation pressure, it actually depends on temperature. So it's not really considered as a very important variable. But yes, even this comes under a variable. And then you have a temperature, right? So if you simply have the pressure, then you cannot really get too much information about the system. Because if you only have pressure, you will not even know what the saturation pressures are, right? So for that, you will definitely need temperature. And once you have temperature, you will get PAS, PBS, right? And then you know by Raoult's law, we have PASXA plus PBS into 1 minus XA. So from this equation, you would get XA, right? I'm just giving an example that let's say you have pressure and temperature. Then how can you get it, right? Then once we have PAS, we can get YA. YA into P is equal to PAS into XA. Now we have PAS, we have XA, so we can get YA. And that's how we have calculated all the variables, right? Let's say they did not give us all these things. Let's say they gave us only pressure and they gave us YA. Okay. So once they give us YA, we can get the pressure. Sorry, we can get the partial pressure, right? We can get the partial pressure in the vapor phase. All right. Then we can equate it with PAS into XA, right? And then we can also use this particular equation. PAS and PBS, they both depend on temperature. So from that, using a certain hidden trial methods, we can get temperature, pressure. We'll discuss about these numerical methods as well while we'll be dealing with this course. So far, you have not learned a lot of things. So I'll not just give you too much information. So basically, the phase rule gives you information about degrees of freedom. So degrees of freedom is the minimum number of variables that are required to define the state of a system. Okay, if you don't have these minimum number of variables, then you'll not be able to define the state of the system. Okay, and this is how the degrees of freedom are calculated. Okay, so variables. Now we come to path variables. So state variables basically tell you about the state of the system. Path variables do not really depend on the state. Instead, they are more importantly dependent on the path. They depend on the paths traveled by the system. For example, let's say this is my initial state. This is my final state. I'll not go into these informations because you don't know what adiabatic processes, you don't know isothermal. So I'll not give you all this information for now. Okay. So let's say this is my state 1 and this is my state number 2. Okay. Now I know the state variables P1 and T1 over here, and I know the state variables P2 and T2 here. All right. So now to move from state 1 to state 2, you can actually travel through different paths. All right. The system, it can actually travel through different paths, all right, to reach this state 2. Now, no matter what path it travels, the variables, the pressure and temperature in state 2 are going to be P2 and T2, even if the system, it comes from this path, or if it comes through this path. In both the cases, the variables here are going to be P2 and T2 only. All right. So that's not going to change. But let's say if they come through this path, then the heat released or the heat added, it might change. And it would change. It would be different. And if it moves from this path, through this path, then heat released or heat absorbed, it would be different. Okay. Similarly, we'll also discuss that even work done differs, it varies. So these variables which depend on the path of the system, the path which the system travels, these variables are these variables are path variables. All right. So we'll further see how work done and heat are two important path variables that depend on the path of the system. Okay. And then we come to thermodynamic equilibrium. So a system in thermodynamic equilibrium needs to satisfy the following criteria. First, thermal equilibrium. That means no heat should be transferred within the system or from the system to the external surroundings or to the system, right? Heat transfer should not take place. Okay. So if this is your system, then no heat should be transferred from, let's say, this point to this point, or it shouldn't be transferred into or out of the system. Okay. So in that case, it is considered to be under thermal equilibrium. Mechanical equilibrium, the pressure should be uniform throughout. Okay, pressure, the total pressure should be uniform throughout. That is the reason when we say we have vapor liquid equilibrium, then we equate the partial pressures of each component and the total pressures. Right? When we equate the partial pressures and the total pressure, then only we get the system of mechanical equilibrium. That's why we say it's in vapor liquid equilibrium. So one of the reasons is that it is under mechanical equilibrium. So that is the equation that we form by equating the partial pressures. Okay. Then the third is chemical equilibrium. Chemical equilibrium in that case. So let's say you have a system where A forms B, right? This is the reaction that is taking place. Now, if this reaction is taking place inside a box, then as time passes by, the composition of A is going to change, right? As time will pass by, or as time passes by, A would keep on reducing, and similarly B, it would keep on getting added, right? So there would be a point of time after which no B would be produced further and no A would be decomposed further, right? So when this time occurs, when this point occurs, then we can say we have chemical equilibrium because we have uniform A and uniform B. So no chemical reactions would take place. Thus, no change would take place in the composition due to these reactions, right? And finally, it should be phase equilibrium. That means no mass transfer should take place between phases. So that's when again we come to vapor liquid equilibrium. So let's say we have A plus B in the vapor phase and A plus B in the liquid phase. So no A from its liquid phase should be transferred to vapor phase. And similarly, no A should be transferred from vapor to liquid. Similarly for B and similarly for the overall system, right? So in that case, we'll consider them to be in phase equilibrium. So these four criteria need to be satisfied when we want a thermodynamic equilibrium to be established within a system. Even if one of the criteria is not followed, then the system is not under thermodynamic equilibrium. Then we come to reversible and irreversible processes. A process that takes place very slowly, passes through infinite number of equilibrium states in between, is known as a reversible process. This process can be reversed at any point of time. Let me give you some information about this. So let's say I want to go from this state to this state, okay? And I have to follow a particular path to reach this state. So let's say in between, I go through A, B, C, these all are different points, D, E, F, G, H, I, J, right? So let's say I'm going to follow this path, right? And my A, B, C, D, E, F, G, H, I, J, all these are my equilibrium states. So that means if I'll go from 1 to A, since both of them are equilibrium states, therefore the system will not really face problem in coming back from A to 1 because the distance between them, the conditions are quite close to each other. So both ways it can go. It can go from 1 to A, it can come back from A to 1. It's easy, right? Similarly, if I am going from A to B, then these two states are close to each other. Therefore, we can easily go from A to B and B to B. All right. So the process that takes place so slowly, the reversible process, it takes place so slowly that it crosses through infinite number of equilibrium states. So basically, you can assume in a reversible process that you take any point, let's say this point you're taking in a reversible process, that point is also going to be an equilibrium state. All right, you can assume that it's that slow that it passes through series of equilibrium states. Okay, so since it is so easy, it's so slow, and since it passes through a series of equilibrium states, so at any point, let's say you want to reverse your process from here, so what will it do? Let's say, okay, let's take this example. So let's say you've reached H and now you feel that no, I want to reverse the process. So you can simply reverse it, right? It can go from H to G, G to F, F to E, and it can go in the reverse order, right? So that is a reversible process. But an irreversible process, in an irreversible process, if you want to go from state 1 to state 2, it will go so fast and without passing through any equilibrium states that it would be almost nearly impossible to reverse it back, right? Because just let's say you have a staircase, all right? Let's say you have a staircase and you want to go from this point to this point. And again, instead of the staircase, another person, he has a slide, right? He has a slide and he has to go from this point to this point, all right? So let's say this point is A, this point is B, A, B, and the person over here would be using a staircase to move from A to B, and the person over here, he would be using a slide to move from A to B, right? Now, let's say if this person, in the first step, he'll move from this staircase to this staircase. Then in the next step, he'll move from this staircase to this staircase, and so on. He'll move, right? Now, let's say if at any point he feels that I don't want to go to B, I want to go back. So he can easily climb the stairs back and go back to A. Why is he able to do that? Because he's passing through a series of planes, right? He's passing through a series of planes. So at any point he can stand and rest, right? He can stand and rest, right? Because it is an equilibrium state, all right? Because here it is equilibrium, right? So he passes through a series of stairs, a series of equilibrium states. And since again, he passes through series of equilibrium states, it is very easy for him to just reverse and go back, climb the stairs back, right? Now that's what a reversible process is. Now just imagine that, let's say these stairs are not actually countable. Let's say there are incountable small stairs, small stairs. So if, let's say, the person is moving down through these stairs, he would not even feel that he's actually going from one stair to another. He would just be moving very smoothly, stopping at each stair and moving, right? So he won't even have a feeling. The stairs would be so thin, right? The thickness of the stairs, it would be negligible, right? So there would be infinite number of stairs between A and B, right? With negligible thickness, all right? So the person, he would actually feel that he's actually moving on a plane. So it's very easy. If a person, he moves on a plane, then it's very easy to just go back, right? But over here, the person is actually moving down a slide. So the person cannot stand at any point and take rest. No, he'll start from here and he'll stop directly here. He cannot just stand and rest at any point of time. So let's say at this point, or let's say at this point, the person decides that I want to go back. So he cannot really climb the slide back, right? So the same happens with a reversible and an irreversible process. An irreversible process, it's a slide, all right? It's a slide. At any point, the system cannot just decide that, okay, I want to go back. It's not possible, all right? But since for a reversible process, at every stair, that means at every equilibrium state, the system can rest. Therefore, the system at any particular equilibrium state can stop and reverse its direction. That is definitely possible. Okay. So that is the difference between a reversible and an irreversible process. An irreversible process takes place so fast. An irreversible process, it takes place so fast that, and it does not really pass through many equilibrium states. So that is why it's not possible to really reverse the process back. And when we talk about a reversible process, so it passes through a series, infinite number of equilibrium states. So it actually can be reversed at any point. Okay, so that's about reversible and irreversible process. Okay, and that's all about a few basic concepts on thermodynamics.